Okay, let's unpack this. You know that feeling when you're trying to research a complex topic online. It's like staring at this mountain of information, trying to figure out which trail to even take first.
Yeah, absolutely.
You follow one link, then maybe another, you hit a dead end, maybe get completely sidetracked. It feels like navigating a massive maze, one step at a time, just kind of hoping you stumble on the insight you need.
That's a great way to put it. And for AI, tackling that kind of open-ended, unpredictable task has traditionally been a pretty significant hurdle. A single AI agent operating, sequentially often gets stuck or misses crucial connections because it can really only follow one thread at a time, limited by its viewpoint and, importantly, its context window.
But what if you didn't have to take just one path? What if you could explore multiple paths all at once? Maybe send out intelligent helpers to investigate different parts of the mountain, have them coordinate and bring back their findings, and then intelligently synthesize all that information much, much faster.
Well, that's precisely what this deep dive is about today. We're exploring the really fascinating world of multi-agent AI systems. And specifically, we're drawing insights from an article by Anthropic detailing how they actually engineered their research feature using multiple Claude agents working together.
Right, the source material, it really takes us behind the curtain, doesn't it? Getting into the actual engineering challenges and the hard-won lessons they learned, bringing this pretty sophisticated system to life.
Exactly. So our mission today is to distill the most important nuggets of knowledge from that article. We want to understand the why behind these systems, like why they're even necessary for these complex tasks, and then the how of their architecture, the key principles guiding their construction, especially through prompt engineering, and the real-world challenges they face getting it to work reliably in production.
Okay, so think of this as your shortcut to understanding this really cutting-edge approach to AI. Let's start with the big question then. Why even bother with multiple agents? What's the core problem that a single agent just struggles with?
Well, the core problem, as the source really highlights, is that tasks like research are inherently open-ended. They're dynamic. You can't just pre-program a fixed sequence of steps because the best path forward depends entirely on what you discover along the way, right?
Right.
It requires continuous adaptation based on those intermediate findings. A single AI agent, even a really capable one, struggles with this unpredictability and also the need to operate autonomously over many steps, making complex decisions without constant human handholding.
Right. It's like asking one person to research every single facet of a, complex global issue simultaneously. It's too much for one brain to handle efficiently and dynamically.
Exactly. And that's where the multi-agent system architecture comes in. The analogy they use, which I think is quite good, is human collective intelligence. Society's scaled capability exponentially beyond what any single human can possibly do, precisely because we specialize, we coordinate, we synthesize knowledge across many individuals. So the same principle applies here. Groups of agents working together can just accomplish far more than individuals working in isolation.
Okay, that collective intelligence idea, that clicks. So what were the specific concrete benefits they actually saw from using this multi-agent approach, according to the article?
So they detail several key benefits. Firstly, it enables agents to operate autonomously for, many turns, making those dynamic decisions based on what they find without needing constant check-ins. Secondly, and this is really powerful for handling huge amounts of information, they cite compression. Subagents explore different aspects in parallel, each managing its own context window, and then they basically condense the critical findings for the lead agent.
Okay. So the subagents are kind of like specialized researchers going deep into a specific area, and they only bring back the executive summary or the key insights to the main researcher. That sounds much more efficient.
It is, and this also provides a strong separation of concerns. Each subagent can be specialized with distinct tools, different prompts, different exploration strategies. This allows for more thorough, independent investigations without the subagents interfering with each other or, getting stuck following the exact same path down a rabbit hole.
Right, prevents them tripping over each other.
Yeah. And finally, they found it significantly scales performance, especially for what they call breadth-first queries. So tasks that naturally require multiple independent directions to be pursued at the same time.
Did they have data, hard numbers to back up that performance claim?
They did, and it's pretty striking, actually. Their internal evaluations showed that a multi-agent system using Claude Opus 4 as the lead agent and then Claude Sonnet 4 models as the subagents. It outperformed a single-agent Claude Opus 4 instance by a massive 90.2%.
90.2%. Wow. That's That's huge. It almost sounds too good to be
It
true.
was a significant finding, yeah.
Yeah.
And they provide a really clear example. Trying to find all the board members of the companies in the information technology sector of the S&P 500 index. The multi-agent system, it successfully decomposed this complex task into subtasks for different agents, gather the info effectively. The single agent trying to do it with sequential searches it failed. Couldn't find the complete answer within the test limits.
Okay, 90.2% is a massive jump. What's the core technical reason they pinpointed for that kind of gain? Is it just smarter coordination?
Well, surprisingly, it kind of boils down to something fairly fundamental, spending enough tokens to actually solve the problem.
Yeah.
Their analysis revealed that token usage alone explains about 80% of the performance variance they saw in these browsing tasks.
Really? 80%?
Yeah. Multi-agent architectures effectively let the system scale the total token usage for tasks that would just blow past the context window limits of a single agent. They allow the system to essentially think and process significantly more information in parallel across different isolated contexts.
Huh. So it's less about the multi-agent system being inherently smarter, like per token, and more about the architecture unlocking the ability to apply a much larger total amount of computational effort and context processing to the problem, just in a distributed way.
Precisely. It unlocks a higher overall capacity for these really complex tasks. However, and the source is very upfront about this, there are trade-offs. There are downsides.
Ah, yes, the inevitable downsides. What were the major ones they identified?
Well, the most obvious one, they burn tokens fast. Their data indicated that agents typically use about 4 times more tokens than basic chat interactions. In these multi-agent systems, they can use around 15 times more tokens than chat.
15 times. Okay, that's a steep price.
It really is. It means they're really only economically viable for tasks where the value and the complexity genuinely justify that significantly higher token cost.
Right. Definitely not for asking, what's the capital of France. So it's really only for those high-value, deeply complex problems where the answer is hard to find.
Exactly. Tasks where the potential time savings or just the sheer difficulty of finding the information manually make that cost worthwhile. They also note that these systems aren't really suitable yet for tasks needing very tightly shared real-time context or intricate dependencies between agents, like a lot of coding tasks, for instance. Agents just aren't currently great at that constant fluid coordination or complex delegation amongst themselves. The coordination is mostly top-down from the lead agent.
Okay. So the sweet spot then?
Valuable tasks. Tasks that involve heavy parallelization, require processing or synthesizing information that just exceeds a single agent's context window capabilities, and need to interact with numerous complex tools in a pretty structured way. That's where they've really demonstrated true excellence.
Okay, that clarifies the why they went this route. Let's dive into the how. What does the architecture actually look like? The mechanics of how it operates day to day or query to query.
So the high-level architecture they designed for the research feature, it uses an orchestrator worker pattern. Basically, think of a lead agent acting as the central coordinator.
The boss agent.
Kind of, yeah. And it delegates specific tasks to a pool of specialized subagents who then execute the work in parallel.
Okay, walk us through it. When I, the user, give it a query, what happens next?
Right, so based on the diagram and the description they provided, it works something like this. User query comes in, the lead agent analyzes it, develops a strategy, and importantly, it uses what they call an extended thinking mode. This acts as a kind of internal scratch pad where it maps out its approach. It thinks through the steps.
Like showing its work.
Exactly. Then it saves that plan and any intermediate findings to a memory module. And this memory step is actually crucial for handling really long tasks. It lets the agent retain context, even when the conversation or its working memory exceeds the standard context window limits, which, can be over 200,000 tokens in Claude Opus 4.
Okay, planning. Saving the plan to memory.
Okay.
What's next? Does it start assigning tasks?
Yep. Then the lead agent spawns specialized subagents. And it can spin up, any number depending on the complexity of the query and the strategy it just devised. Each subagent gets a specific, focused task.
And these subagents, they work independently, or are they chatting with each other?
Mostly independently. Each subagent performs actions relevant to its task, like, say, conducting web searches. Critically, they evaluate the tool results they get back. They use this thing called interleaved thinking, basically processing the output, identifying information gaps or issues, and then refining their next steps or queries based on that. Then they return their findings back up to the lead agent.
So the lead agent is getting all these reports back, maybe from multiple subagents working at the same time. What's it do with all that incoming info?
It synthesizes those parallel results. It combines and organizes the findings from all the different subagents.
Hmm.
And based on this synthesized information, the lead agent makes the decision. Have we gathered enough information to answer the query? Or, is more research needed?
Ah, the iterative loop.
Exactly. If more is needed, it can refine the original strategy, it can spawn additional subagents with new tasks, or maybe guide existing ones in a different direction. This is that dynamic part, right? It allows the system to adapt based on discoveries, much like a human researcher would.
Got it. It keeps iterating until it feels confident it has the answer, and then what? How does it wrap up?
So once sufficient information is gathered, the system exits that research loop. The consolidated findings are then passed to a separate, specialized agent. They call it a citation agent. This agent's sole job is to process all the gathered documents and the final research report to find the specific locations or sources for citations, making sure claims are properly attributed before the final answer gets presented back to you, the user.
That sounds much more sophisticated and, well, dynamic than something like a traditional RAG system, which mostly just retrieves static chunks of text based on similarity, right?
It is. And they specifically contrast it with RAG. RAG typically relies on that static retrieval of pre-indexed chunks. Their system is designed as a dynamic, multi-step investigation process that actively adapts based on findings, analyzes results as it goes, and performs actions like targeted searches and synthesis. It's not just looking up information, it's actually conducting a multifaceted investigation.
Okay, so the architecture makes sense on paper, but bringing something this complex with multiple independent agents trying to coordinate to life must have been a massive engineering challenge. The article mentioned rapid growth in coordination complexity and unexpected emergent behaviors.
Oh, absolutely. They really highlight that prompt engineering became their primary lever for managing these complex behaviors. Because when agents operate autonomously, they can do unpredictable things, like, spawning dozens of subagents for a simple question, or getting stuck in endless loops, or using tools completely incorrectly. They had to learn and instill key principles to guide these agents effectively.
Okay, so what were some of those key principles for prompt engineering that they discovered? What worked?
Well, one of the first and most crucial was think like your agents. They built detailed simulations to observe agent behavior step by step, watching exactly how prompts affected the agent's actions and where they failed. Like, seeing an agent search endlessly or consistently pick the wrong tool was absolutely essential for understanding and fixing the underlying issues in the prompts.
It's like getting a really detailed log of your research assistant's thought process, so you can see exactly where they got tripped up or went off track.
Exactly like that. Another key principle was teaching the orchestrator effective delegation. The lead agent needed to give subagents really detailed, unambiguous task descriptions. Things like outlining the objective, the required output format, what tools or sources were acceptable, and setting clear boundaries. Vague instructions, like just saying, research the semiconductor shortage, apparently led to chaos.
Chaos how?
Well, agents duplicating work or missing crucial areas. They gave an example where one agent focused on the 2021 crisis, while two others redundantly researched 2025 supply chain forecasts. They needed that precision to divide the labor effectively and avoid waste.
Right, preventing that kind of redundant effort seems key to efficiency. What else did they learn on the prompting front?
They learned to scale effort proportional to query complexity. The agents needed explicit rules embedded right in the prompts, dictating things like how many subagents to spawn, how many tool calls to make, how deep to go based on whether the query was simple fact-finding or a comparison or really complex multi-part research. This basically prevented the system from over-investing resources, like burning tons of tokens on relatively easy tasks.
So they built the intelligence to kind of judge the complexity of the task right into the initial prompting itself? Smart.
Yes, adding that layer of sort of metacognition. Tool design and selection were also absolutely critical. The interface between the agent and the tools it can use is just vital. Agents needed robust heuristics for choosing the right tool, like examining all available tools first, carefully matching the tool's function to the user's intent, understanding when to use the web for broad exploration versus preferring specialized tools. They found that poorly described tools could easily send agents down completely irrelevant paths, wasting a lot of time and tokens.
So the description of what a tool does is almost as important as the tool's underlying function, at least for the agent using it.
It really is. And here's where it gets, really interesting. Letting agents improve themselves. They found that the more capable Claude 4 models could actually diagnose why they failed at a task and then suggest improvements to their own prompts or even the tool descriptions they were given.
Wait, hang on. An AI agent improving the instructions and tools for other AI agents, that feels like a pretty significant step towards, I don't know, autonomous self-improvement in these systems. Was that something they planned for, or did it just emerge?
That was certainly one of the most surprising and exciting findings from their work based on the article. They even created a dedicated tool testing agent. Its job was to test tools that agents struggled with, figure out why, and then rewrite the tool's description to make it clearer and more accurate for future agents.
And did that work?
Get this. The tool testing agent's rewrites resulted in a 40% decrease in task completion time for future agents using the improved description.
Wow.
Yeah.
40%.
Yeah. It's a concrete example of the system automating part of its own prompt engineering and tool maintenance process. Really fascinating stuff.
Incredible. Okay. What other core prompting strategies emerged from all this work?
They guided agents to start wide, then progressively narrow down. Kind of mirroring good human research practice, right?
Yep.
Agents were prompted to begin with short, broad queries, evaluate those initial results, and then progressively refine and narrow their focus based on what they found. This strategy helped avoid the problem of agents getting stuck with few or no results because their initial query was just way too specific.
That makes so much sense. You don't ask for the exact number of, I don't know, blue widgets sold in October in Berlin on the very first try. You ask about global widget sales, then maybe narrow to Europe, then Berlin, then potentially October.
Exactly that kind of iterative refinement. They also found that extended thinking mode we mentioned earlier to be incredibly valuable, not just for the lead agent's planning. For the sub-agents, it was used after they got tool results. It gave them a space to evaluate the quality of the findings, identify missing information, and refine their next query or action before just blindly making another tool call. This explicit thinking process improved instruction following, reasoning, and just overall efficiency.
It's like giving them a dedicated space to pause, process the information, and maybe sketch out their next steps before acting. Makes sense.
Yeah, it helps them reason explicitly and avoid just jumping straight to an action that might be suboptimal. And finally, maybe one of the biggest drivers of the speed increase they saw was implementing parallel tool calling. Their early prototypes apparently did sequential searches, which was a huge bottleneck. So they introduced 2 layers of parallelization.
2 layers.
Yeah. First, the lead agent spawning multiple sub-agents they mentioned, typically 3 to 5 running simultaneously. And second, allowing the sub-agents themselves to use multiple tools, often 3 or more in parallel within their own process.
Whoa. Okay, so not just multiple scouts out there, but each scout can use multiple different resources or methods at the exact same time.
Precisely. These changes, enabling both parallel sub-agents and parallel tool use within them, cut the total research time by up to 90% for complex queries. 90%. It allowed them to accomplish dramatically more work in minutes compared to the earlier, more sequential approach.
That level of speed up is just, it's a game changer for these complex tasks. So summing up the prompting strategy, it sounds like it's less about rigid, fixed rules and more about instilling good heuristics like methods derived from how skilled human researchers approach complex problems.
Yes, exactly that. Teaching them how to decompose questions, how to evaluate the quality of sources, how to adjust their approach dynamically based on findings, understanding when to go broad versus deep. Those human-like strategies encoded into the prompts, alongside, of course, explicit guardrails to prevent undesirable behaviors like infinite loops or inappropriate tool use.
All right, so they've designed this sophisticated architecture, figured out how to prompt it effectively, and achieved these really impressive performance gains. But how do you actually know if it's working correctly and reliably? Evaluating these multi-agent systems sounds like a whole new kind of challenge in itself.
It really is, because, traditional evaluations often assume the AI will follow a single predefined optimal path. But these systems are inherently non-deterministic. Different agents, or even the same agent run twice, might take entirely different yet equally valid paths to reach the same goal or synthesize the same information. You can't just check if they followed your specific pre-planned steps. You have to evaluate the quality of the final outcome and sometimes even the intermediate process itself.
So what were the key evaluation lessons they learned then? How did they tackle that?
Oh, first, and maybe a bit counterintuitively for such complex systems, start evaluating immediately with small samples. They found that even early changes could have massive impacts on performance, like a single prompt tweak could jump the success rate from 30% to 80%. So testing with even a small representative set of maybe 20 real-world queries was enough to quickly determine if a change mattered significantly. You don't need to wait for massive, perfectly balanced test suites right at the beginning.
Right. Don't let perfect be the enemy of the good, especially when it comes to that early feedback and iteration cycle.
Exactly. Second, they found that LLM as judge scales well when implemented carefully. Since research outputs are typically free-form text with no single correct answer, using another LLM to evaluate the output against a rubric is actually a pretty natural fit. They used an LLM judge with criteria covering things like factual accuracy, citation accuracy, completeness, source quality, and even tool efficiency. A single LLM call providing scores and a pass-fail grade worked well and showed good alignment with human judgment, especially for test cases where there was a clear factual component the LLM judge could verify.
So an AI evaluating the work of other AIs using a predefined set of criteria. That's quite meta, but it sounds incredibly efficient for scaling up evaluation effort.
It allowed them to scale evaluation to hundreds of outputs very quickly. But, and this is a critical caveat, they make human evaluation catches what automation misses. People actually testing the system found edge cases and subtle failures that the automated LLM judge didn't always spot. Things like subtle hallucinations on unusual queries, or complete system crashes under very specific conditions, or biases in source selection.
Like the example you mentioned earlier, maybe the agents sometimes preferring those low-quality SEO farms over more authoritative sources that a human tester would immediately flag.
Precisely that. That specific example was a finding from human testers that led directly to a crucial fix in the prompt design. So manual testing, even alongside scaled automated evaluations, remains essential for catching those tricky emergent behaviors, subtle biases, and unexpected system failures. It really highlights that these prompts are more like frameworks for complex collaboration between agents, rather than just rigid step-by-step instructions. And those interactions can lead to really unpredictable outcomes sometimes.
Okay, so they figured out the why, the how, the prompting, and the evaluation. Now comes what sounds like the truly brutal part. Production reliability. Taking this complex, non-deterministic system from a working prototype to something that runs reliably at scale for actual users.
Yeah, they described this as initially thinking it was the last mile, but they state it ultimately became most of the journey. It was significantly harder and took way more effort than they initially anticipated.
Why was that gap? Why was getting it from prototype to production so much wider than they expected?
Several key reasons came up. Firstly, agents are stateful and errors compound. These things run for a relatively long time, right? Maintaining state across many steps and interactions. An error that happens early on isn't just a single failure point. Because of that statefulness, it can unpredictably derail the entire long-running process in ways that are really hard to predict. And you can't just restart a multi-step agent process cheaply if it's halfway through a complex task for a user.
Right. That makes sense.
So they needed robust systems to actually resume from where the agent was when an error occurred. They ended up combining the AI's inherent adaptability, like designing prompts so the agent can understand a tool failed, and maybe try an alternative approach with more traditional software safeguards like retry logic and checkpoints.
So the system needs to be resilient enough to handle those hiccups mid-task and allow the agent to kind of recover gracefully without losing all its progress.
Yes, building that resilience was absolutely key. Debugging also required entirely new approaches. That non-deterministic nature makes traditional step-by-step debugging really difficult. When an agent doesn't find information it should have found, is it because of a bad query it formulated? A poor source it chose? An issue with the tool itself? It's hard to pinpoint the root cause just by looking at the final output.
Yeah, I can see that.
So they implemented full production tracing to record every action and observation an agent made. This allowed them to go back and see why a specific failure occurred. They also started monitoring higher-level agent division patterns and interaction structures, like the flow and types of interactions between agents while respecting user privacy, of course. This helped them diagnose root causes at a more abstract systemic level.
That's a clever approach, looking at the structure of the interaction rather than needing to parse the potentially huge amount of content from every single step.
Exactly. It's essential for understanding those systemic issues. Yeah. And then deployment itself also needed very careful coordination. Remember, these are long-running, stateful processes handling live user queries. You can't just shut everything down and deploy a new version of the code. That would interrupt active agent runs, potentially losing user work.
All right.
So they implemented techniques like rainbow deployments, or you might know them as phased rollouts, basically gradually shifting traffic to the new version while the old one continues to run, allowing active agents on the old code to complete gracefully before that version is finally retired.
Okay, like changing the tires on a moving bus, but for extremely complex AI systems.
A very high-stakes version, yeah. And finally, they identified a limitation in their current design. Synchronous execution creates bottlenecks. At the moment, the lead agent largely waits for subagents to complete their tasks before it synthesizes the results and decides on the next step. This simplifies the coordination, sure, but it limits true parallelism and information flow.
How so?
Well, the lead agent can't effectively steer subagents mid-task based on early results from other agents, and the subagents can't coordinate or share information directly with each other easily. Moving to a fully asynchronous execution model would unlock significantly more parallelism, but it adds substantial engineering complexity. Things like coordinating results arriving at different times, managing distributed state consistency, handling error propagation across all these concurrently running processes. It gets complicated fast.
But they think the performance gains might be worth tackling that complexity later.
That's the indication, yeah. They expect the performance gains will likely justify tackling this complexity down the line.
So it sounds like even with all these advancements and the lessons they've learned, there are still fundamental architectural evolutions they see on the horizon for really maximizing efficiency and coordination.
Exactly. That gap between a successful prototype and a truly reliable production system was wider than they anticipated, largely because of these compounding errors and emergent behaviors you get with stateful non-deterministic agents. Achieving reliability just requires this deep combination of engineering rigor, extensive testing, incredibly detailed prompt and tool design, robust operations, and, critically, deep cross-team understanding of the agent's capabilities and their potential failure modes.
Wow. It sounds like they learned a tremendous amount on this whole journey to build a production-ready multi-agent system. But ultimately, what's the real-world value here? What impact are these systems actually having now that they're in users' hands?
Well, the article reiterates that they have proven genuinely valuable for those difficult, open-ended research tasks we talked about at the start. And the impact reported by users, as summarized in the source, sounds pretty significant. People are using Claude's research feature to uncover business opportunities they might have otherwise missed, or navigate complex healthcare or financial options, resolve really challenging technical bugs. And perhaps most importantly, they report users saving up to days of work by rapidly uncovering connections and information they just wouldn't have found efficiently on their own.
Days of work saved on a single query. That's a pretty tangible return on investment for tackling that kind of complexity and cost.
It absolutely is. They even list the top categories of problems users are applying this to. Developing software systems accounts for about 10% of use cases. Professional and technical content creation is 8%. Business growth strategies, another 8%. Academic research and education is 7%. And researching people, places, or organizations is about 5%.
So clearly useful across a pretty wide spectrum of complex, information-heavy domains then.
Yes. The conclusion they draw is a strong one. These systems can operate reliably at scale when built with the right engineering principles and rigor, and they are demonstrably transforming how people approach and solve complex problems that were previously just very time-consuming and difficult to navigate effectively.
It paints a powerful picture, doesn't it? Coordinated AI tackling problems that were previously just too unwieldy for single agents or even traditional computational methods. So, okay, let's leave you, our listener, with this provocative thought. Considering that these multi-agent systems are proving so effective at parallelizing complex research that they can even self-improve aspects of their own operation like tool use and prompting, and that they seem limited primarily by token cost and the remaining engineering complexity of even better coordination. Where does this leave us? What previously insurmountable problems could this kind of coordinated AI unlock in the future? And maybe more personally, how might this fundamental reshaping of the research and discovery process change our own role, our own value in the journey of learning and problem solving?
That's something truly worth considering as these capabilities become more widespread, isn't it?
Indeed. Well, thank you for joining us on this deep dive into multi-agent AI systems and the really valuable lessons learned building them.
We've unpacked the why, handling complex dynamic tasks better than single agents.
The how, that orchestrator-worker architecture, and the iterative research process.
And those significant engineering lessons learned in bringing them from just a prototype to reliable production.
And we hope it gives you a clearer picture of this exciting development in AI and what it might mean for tackling complexity in your own world. Keep thinking about that provocative question, what these capabilities mean for the future of research and problem solving, and for us.
Until next time.